In this example, we'd like to try to find a power series solution to this first-order differential equation by using the recurrence relation method that we've been studying in this course. So let's start by writing down a couple pieces of information. Let's recall that a power series representation of a function y centered at 0, that's the initial point of our initial data in our differential equation. This is just given by a sub n times x to the power n. And here our goal, if we want to be able to describe this function, our goal is to find the coefficient sequence a sub n. So we want to be able to find a sub n. So solve for a sub n in some sense. Remember that the derivative y prime is written as a sum n from 1 to infinity n times a sub n times x to the power n minus 1. This is just done by expanding out the terms of the power series y and then taking the term-by-term derivatives and writing it back in sigma notation. So if you don't believe this, please pause, make sure that you can compute the derivative, and then you can restart at the next stage here of our problem. And the next stage is to now plug in these two formulas for y and y prime into the equation of the differential equation, so into the formula for the differential equation. Here's what we get. Y prime plus 3x times y becomes the sum, just replace y prime first. So this becomes the sum, n from 1 to infinity, n times a sub n, x to the power n minus 1, plus 3 times x times the sum, n goes from 0 to infinity, a sub n, x to the n, and this whole thing should equal 0. And now we know that what we would like to do is write this as a single summation and then try to solve for the coefficients, right? We're going to end up getting a recurrence relation for the coefficients. The first thing that has to happen is this has to go in here. Now, I've drawn it like this. The whole thing has to go in, but these are going to go two different places. The x gets grouped with the x, right? And the 3, that's just a constant, that gets grouped with the coefficients. Alright, so this is kind of weird, this picture I've got here. But this now becomes the sum, n from 1 to infinity, n times a sub n, x to the power n minus 1, plus the sum, n here is going from 0 to infinity, 3a sub n, x to the power n plus 1. And this all equals 0. And what we would like to do at this point is get these so that they both start with the same index, right? They have to both start with the same index. So one way to do this one's starting with the power x equals 1, right? So what we can do, one thing we can do here is we can knock this one down, right? So we can replace n with n minus 1 here. But then down here this has to go up, right? So this would start at n equals 1. And we can do the exact opposite over here, right? So this one can go up 1. So this n will be replaced with this n minus 1 will be replaced with n. And so what that means then is that these n's will become n plus 1, and this one has to go down 1. So this will start at n equals 0. So in some ways, manipulating the index when it's necessary is kind of the hardest part here. And so this now becomes the sum. N goes from 0 to infinity. This one's gone down, so each of these go up. This is now n plus 1, a sub n plus 1, x to the n, plus over here, this one starts at 1. Notice I had to go up 1. And these ones have to go down 1, right? So this is 3, a sub n minus 1, x to the n equals 0. So these all went down 1. And now we can combine these, though, almost. We're not quite ready, because this one has an extra term. It starts at n equals 0. This one starts at n equals 1. So the next thing we have to do is take away the n equals 0 term from here, right? So when n equals 0, what does this one give us? It gives us 1 a sub 1. So that's just a sub 1. Plus the rest of it, right? The rest of it happens, we start with n equals 1 to infinity, and then our formula holds, right? So this is n plus 1, a sub n plus 1, x to the n, plus over here we still have our term here, n equals 1 to infinity, 3 a sub n minus 1, right? X to the n equals 0. All right, and this whole sum has to equal 0. Well, how can the whole sum, well, let's combine these two first, right? So this now becomes, we have our a sub 1 just kind of hanging out, and then we have this sum, n goes from 1 to infinity of, the coefficients are n plus 1 a sub n plus 1 plus 3 times a sub n minus 1. X to the n equals 0. Alright, and so now we have some information. So remember, for this entire sum to equal 0, what does it mean? It means that all the coefficients have to equal 0, right? We set all the coefficients equal to 0, and that includes this one out here. So this one out here must also be set equal to 0. And at this point, we can also go up and we can look at this piece of information here, right? Y sub 0 equals 8. So I'm going to write this over here, but y of 0. Well, according to our power series, that's the sum. N goes from 0 to infinity. A sub n times 0 to the power n, right? Well, 0 to the 0 we're going to regard as equaling 1 here. So this actually equals a sub 0 plus 0 plus 0 plus 0, etc. Alright, and so y sub 0 is equal to a sub 0. And so this piece of initial data, this will always be the case. This piece of initial data right here tells us that a sub 0 is equal to 8. That's going to be part of, it's going to be very important, right? It's going to be part of our solution for the coefficients here. So let's gather everything we know. We just wrote down a sub 0 is equal to 8. We also know a sub 1 is equal to 0. And then from the recurrence relation, we know all of this. We know that for n bigger than or equal to 1, the rest of this is true, right? So this gives us the recurrence relation. I'll write it in 2 steps. But n plus 1 times a sub n plus 1 plus 3 times a sub n minus 1 equals 0. This is true for n greater than or equal to 1. And we can solve this for the larger index, right? So a sub n plus 1 is then equal to negative 3 over n plus 1 a sub n minus 1. Again, for n greater than or equal to 1. Now sometimes what I like to do is, again, make a shift here to just make this one be n, right? Just make n equal n. Sorry, make your n plus 1 become n. So what am I doing? I'm shifting everything down one, right? So this then said, but that means this has to go up. So what does this mean? Well, this tells us, I'll write it over here. This is really truly our recurrence relation now. This one then says that a sub n is equal to negative 3 over n, down, times a sub n minus 2, the one that comes 2 previous to it, right? So n minus 1 is 2 previous to n plus 2 plus 1. And this now only applies for n greater than or equal to 2. Alright, and so notice that when it's written this way, we have covered all the indexes, right? All the indices. We have a sub 0 is 8, a sub 1 is 0, and then from then on, these change by every other one is related to the one that comes 2 before it, right? So now we can start writing down some things. First of all, if a sub 1 is 0, then based on our recurrence relation, that means that a sub 3 is 0, 2 after it, because it's 0 times something. A sub 5 is 0, etc., right? So this, just based on this, we can see that a sub 1, a sub 3, a sub 5, a sub 7, all the way out, right? A sub 2n plus 1, all the odd ones are equal to 0. So our power series is not going to have any odd terms. It's only going to have even terms, right? So now what are those even terms going to be? Well, let's write out a couple formulas here. We know that a sub 0 is 8. We go to the next one, a sub 2. A sub 2 is negative 3 over 2, based on our formula, right? Based on our recurrence relation. It's negative 3 over 2 times a sub 0. Well, that's negative 3 over 2 times 8. All right, let's go to the next one. A sub 4. We're going in steps of 2 because that's what our recurrence relation tells us to do, right? So a sub 4 is then negative 3 over 2 times a sub 2. But what's a sub 2? It's right here. This goes in here, right? And so what do we have now? We have negative 1 squared times 3 squared over 2 squared times 8. All right, let's do one more. Maybe we can see the pattern, but let's do one more. If a is equal to 6, what do we get? Negative 3 halves times a4. Well, what's a4? It's all this that we just solved for, right? So now we have another negative, another 3, another 2, right? So now we have negative 1 to the third, 3 to the third, over 2 to the third, times 8. All right, and now we can see exactly how this is going. This is 2 times 0, this is 2 times 1, 2 times 2, 2 times 3. If we write this as a sub 2 to the n, then our formula is that this is going to be alternating, right? Negative 1 to the n, 3 to the n over 2 to the n times 8. All right, and at this point, because there's an 8 here, I mean, let's just leave it like this, okay? You can combine the 8 with the 2 because 8 is 2 to the third power, but let's not do that. But this is going to now be our coefficient sequence for our power series solution, and we have to be very aware that we have now done this, right? We only have the even terms. That means that in our sequence we only get the even terms, or in our series I should say, we only get the even terms. So if we scroll back up to where our series was defined, this series we're not going to have all the terms, we're only going to have the even ones. So we need to deal with that the same way we did down below, right? So here's the last step. We just plug in this formula and we see that our power series solution is that y is equal to the sum. N goes from 0 to infinity. A sub n, that's the formula we just found. Negative 1 to the n, 3 to the power n over 2 to the power n times 8 times x to the power, in this case it's going to be 2n because those are the only coefficients that we have. So x to the power 2n. Alright, and so this is our power series solution to the given differential equation with the initial data, the given initial data.